Hello everyone and welcome again. Let us discuss our previous topic. What we were discussing is about this conditions to follow that how a given transformation is going to be canonical transformation. And then we discussed about this some Poisson bracket topic, and we have gone through some properties of Poisson bracket and some fundamental Poisson brackets, and then we had decided to do certain problems. And before that uh, so we were about to look one important concept in Poisson bracket, that was the invariance of the Poisson bracket under canonical transformation. So as you know, canonical transformation is to when you transform your old coordinates to the new coordinate, providing certain Hamiltonian canonical equations, and the modified Hamilton principle are going to be preserved, then your transformation is the canonical transformation. So if under canonical transformation from old coordinates small qp to new coordinate qp, then the Poisson bracket of the two function and are going to be invariant. That means invariance means that is going to have the form of that is going to be same. So let's start with that, saying that this we have a pair of function f and g which depends upon either qp or qp. So like we have first transformation from this q from this old coordinates to my new coordinate, and then from old coordinates to the my new coordinate p. Okay. So if you write the Poisson bracket of this f and g with respect to the canonical old variable, that is my base is the old variables, this is small q and small p. So then you write from the definition of the Poisson bracket that you first differentiate with respect to q, and then the second with respect to second function, first with respect to q and then second function with respect to p, and then you repeat the first with respect to q and second with respect to q. Okay, this is how you define the Poisson bracket. That is Poisson bracket is a mathematical operation that gives you that how the two functions f and g are going to behave when you change their variables on which they depends, canonical variables q and p. So and then we consider this function, this my function g, which depends upon my new canonically transformed variables, that is q and p. So if what I'm going to do is I'm going to find this g with respect to pi, and then g with respect to qi. Okay, so first my g depends upon q and p, so I can, if I have to find this g with respect to pi, so what I'm going to do is I'm going to do the g with respect to pi. So because g depends upon this q and p, so g with respect to capital Q again, and then q, this q with respect to my this pi. Okay, so this with respect to pi, and then g with respect to p, and p with respect to this pi. Okay, similarly we can write for this g with q, okay, small qi. So then g with respect to small qi, so because g is a function of q and p, so g with respect to q and g with respect to p, and then q with respect to q, because we had to partially differentiate with respect to a small q, and this is how we have. Now using these two, there's delta g upon delta q, and this delta g upon delta pi here in this case in equation 1. So what I'm going to get is delta f upon delta qi, and this whole expression to be put here in place of delta g upon delta pi, and similarly for delta g upon delta qi. So you have delta f upon delta pi, and the whole expression of delta g upon delta pi is written as, because f g is because f g qp is nothing but sum over this I, delta f upon delta qi, and delta g upon delta pi, and minus delta f upon delta pi, and delta g upon delta qi. So delta f upon delta qi is there, and in place of delta g upon delta pi, I am writing this delta pi whole this thing, this expression, and then we have delta f upon delta pi here, and in place of delta g upon delta qi, I'm going to write this whole expression here. Okay, this you can see here. Now what I'm going to do is I'm going to take this delta g part outside. Okay, so I have delta g here and delta g here, 1 2, so delta g upon delta qj here, delta g upon delta qj here, and delta g upon delta pj here, delta g upon pj. So I'm going to take the common delta g upon delta q and delta g upon delta p. So if I take common delta g upon delta q here, so I'm going to get this term here, and then I'm going to have this term here similarly, and the other term with delta g upon delta qj is here, so that is going to be minus delta f upon delta pi, minus delta f upon delta pi, and then delta q delta, and then not this one, because I'm considering this term, so this is the first term, and then the second term will be delta q upon delta qj. Similarly, if you take all together the term with delta g upon delta pj, so delta g upon delta pj, if you take common here, and then the first term will be with this, and this is going to be this, and the second term will come upon from here and here. Okay, so this is what we have. So now you can see that this is common. This is what we have is here is you can see is f with respect to q and q with respect to p, and then f with respect to p and q with respect to q. So this is going to give me this Poisson bracket of the first function, and this is second function, and the same way this is f with respect to q and p with respect to p and q. This is the Poisson bracket of the first function and the second function. This is f and pj. Okay, so my the Poisson bracket of the two function in my old coordinates qp, the base is qp, all canonical variables, is going to be this expression number 4, which is in terms of f with respect to this and f with respect to this. So base is still, now our base is still the old canonical variable, so we need to figure out that this is going to be, if this is fg is or say I want this fg is has to be, the base has to be qp. Okay, that means so one base is there, q is there for this, and 1p is there. Okay, 1p is there. What I need is I need to figure out about these two components to be in terms of, this must comes out to be delta f upon delta p, because then I'm going to have q and then p, and this must comes about delta f upon delta q, because p is already there. Okay, so if I write this is Poisson bracket, so you write the delta f upon del q, and then you have delta g upon del p, and the second term will be minus delta f upon delta p and delta g upon delta q. So I have delta g upon delta q, I have already delta g upon delta g upon delta q I have already, so I need, so that means this delta f on delta p, this is going to be my this term. Okay, this term is going to be my delta f upon delta p, and then this term delta g upon delta p is already there, this term if you see. So that means my this Poisson bracket fgp is going to be my delta f upon delta q. So then I can write this whole expression, equation 4, as equal to fgqp. Okay, then there is going to be the invariance. So now to find out this, so do some mathematical replacements. So if I want this f to be replaced by qi, if replace this f to be qi, and g to be f, okay. So then what I have is this here, g is replaced by f, and f is replaced by q. Okay, again I have here g is replaced by f and f is replaced by q. Now you know that this q is 0, the Poisson bracket of the same variable function is 0, and then this QP is going to be delta Ij. Okay, so now the life is simple. So now this QQ is 0, and then this is going to be delta Ij with delta Fe. So this is going to be, when I equal to j, this is going to be 1. For I equal to j, this is going to be 1. So then this is j becomes my I. So this is delta F upon delta Pi. So QF with QP is delta F upon delta Pi. One term is that. Now if I reverse this, F to Q and Q to P, so I get a negative sign. Okay, so I write F QP QP, then this here I'll get a negative sign. So this negative sign is here. So this is equation number 5 that I'm going to put here. So you see that FQI is I'm going to put here in this FQI. I'm going to put here is this FQI, so if QI minus delta F upon delta Pi. So that is what I want, delta F upon delta P. Okay, now in the same way, if I replace by now this was F, my F jo hai, this is my F by P, and this G by F. So now F by P and G by F. So if I do this, now you see that the same as we did for Q case. So PP is going to be 0, and this is going to be my delta Ij, because this is P and J. This is fundamental of the Poisson bracket. So but this because this is Pj, and this is going to be minus, because you know that QP is delta Ij and PQ is minus delta Ij. So you have QP here, PQ here, so I am going to have minus delta Ij. So this PF is my delta F upon delta Qi, and if I reverse this, so then I have FPI is this negative sign with negative sign will go off, and I have this FPI is FIQ. So now if I put these equation 5 and 6, as I told you in this equation number 4, if I replace by this and this, what I'm going to get is, so remember that this here I have the base as QP. Okay, now if I put this, one is coming out to be delta F upon delta Pj, this, and the second is delta F upon delta Q, is this thing. Okay, so now you see what is coming out. See, if I say this negative outside, so this negative outside, so what we get is this negative outside, delta G upon delta Q. So first with respect to Q, and second with respect to P, and then will become minus because negative is outside, and the first with respect to P, and the second with respect to Q. Okay, so now this is the Poisson bracket of G and F, with the base is capital Q and capital P. So this is GF, capital Q and capital P. So if I reverse this G to F, so then become FG Q to P, and on the left hand side I have FG with the base of the old coordinates. So when you do the canonical transformation from the old coordinates to the new coordinates, then the Poisson bracket of the two function which are the variables depends upon the canonical variables, they are also going to be invariants under the canonical transformations. This is what we had to prove that, and then you see that if the simple mathematical shifting and some properties you applied, then you get the invariance of the Poisson bracket under the canonical transformation. Okay, so this we have to remember that if the transformation is the canonical, then if you have any two function which depends upon this canonical variables, then their Poisson bracket are also going to be invariants under that transformation. So and then if you remember that to find out that a given function or transformation, not a function, transformation is canonical, how to find out? So earlier we had to condition that you had to follow some partial differential, and so if they are equal, you have 4 partial differential, if equal, then the transformation is going to be canonical. And then if the transformation is going to be the perfect differential, then again that is going to be canonical. And the third thing is, if you find out the Poisson bracket between the transformation, and that comes out to be like if you have QP is delta Ij, because QQ, and because what you're doing in canonical transformation from QP to qt or from a capital qp to a small qp, whatever your transformation is that. But if you find out, because qq is 0, pp is 0, this is standard, and qq and small qp is also going to 0. So if I have been given the transformation of this q, that is q depends upon qp, and you have been given p, that is p which depends upon qp, so then this qq, this first will be 0, but the second has to be delta ij, that is going to be 1, or if you find out pij, that is going to be -1. So if this follows, then this transformation is going to be the canonical transformation. Or if you have been given that q in terms of qp and p in terms of qp, then you try to find out, because these were 0, and then you try to find out either this qp and pj, this is going to be pq, so this is going to be negative here, and then okay, so this is going to be negative, and then you find qp, this is going to be delta ij. So if this is 1, then this transformation is going to be the canonical transformation. Okay, this is fine, and these things are, I think, and the second thing is, whatever the base is, you have to look for the base also, whether you are calculating in terms of because the transformation equations can be like any in terms of any variables, in variables q, p, and q and p. So transformation will be the mixed. Okay, so then you have to see for that what variable you are choosing the basis, with what respect you are defining your Poisson bracket. Okay, then you have to look for. So now let us try to go with some example for that. So first example is like show directly that the transformation is canonical. This is the transformation is given, q, capital Q and capital P. The transformation is given. So we have to find that whether this transformation is canonical or not, and then we have to find the generating function also. Okay. So let us go with the first method, that is if the transformation is a perfect differential. If the transformation is perfect differential, then I am going to get that this transformation is going to be the canonical transformation. Okay, so first I am going to find is this capital dq, because I have q here. Okay, is given, so I'm going to find capital Q. So this is what I am, the capital Q. So then I had to find this first with respect to, so differentiate with respect to Q. So if you differentiate this with respect to Q, and then with respect to P, so because Q contains Q and P, so with respect to Q and then with respect to P. So when you differentiate with respect to Q, so then you have log of this thing is going to be 1 upon 1 by Q and sine P. So this is going to be Q upon sine P. You have a Q upon sine P. Okay, either you do with and then you differentiate with respect to Q, that is sine P upon Q. So whether you're doing it with respect to Q, that this is going to be 1 upon Q, because sine P is depending upon P. So this is going to be sine P, and then del Q of 1 by Q. So this is going to be sine P, and this is going to be minus 1 upon Q square. Okay, so this is sine P minus Q square dq, and then the second time you differentiate with respect to P. So when you differentiate with respect to P, so this term is going to be there. So 1 upon 1 by Q sine P. So that is this is there, that's why it is common, and then you are differentiating with respect to P, that is sine P by Q. So when you're differentiating with respect to P, then 1 by Q is same, but sine P with respecting P, that is going to be the cos P, the sine P by cos P, and this is going to be dP. So this is how you are doing dq. This is finding dq. So this is common. So now if you take inside, this is going to be cancelled, and this q will going to be minus 1 by Q dq, and then this Q will cancel here in this case. Now in this case this q will cancel out, and then you have cos P upon sine P is going to be the cot P, and then you have dP. Okay, so this is your dq. Now I have to multiply it by this P. Okay, so my P is Q cot P, so I multiplied by Q cot P. This whole thing is to be multiplied by Q cot P. Okay, now you see that. So this q will cancel out. I have minus cot p dq, and then this cot p is, this is going to be, this q is there, so this is q cot square p dp. Okay, so from the second term, when this is multiplying by this, so this is going to be the q cot square p and dp. So now I have p dq here, so this we have calculated p dq. Now I'm going to subtract this from the p dq, small p dq. So this is p dq minus this capital P dq we have calculated. So this is p dq, and then this is minus p dq. If you do this is, so if this becomes positive, this becomes positive cot p dq, and then this becomes negative because I have minus here, so this is minus q cot square p dp. Now you can see one thing, that is p dq is there, okay, and then this is cot p dq is there. Now I can write this cot square p, this cot square p, as cosec square p minus 1. Okay, so for doing this, I can have this q minus minus plus, this is going to be q dp. Okay, so now p dq I already have, and then from here I take q dp. So this becomes my perfect differential dqp. Okay, now what I have is left is this term, this is qp dq, and the second term from here is q cos square p dp with negative sign, so q cos square p dp. So this all together give me this perfect differential of q cot p, because this is going to be cot p dq, this one first term, and the second term, if you keep q constant and then you differentiate d cot p, that is going to give minus q square cosec square p dp. Okay, so now these two are perfect differential, qp and q cot p. So I have my perfect differential. This is p dq minus p dq is my perfect differential. This is my df. Okay, so this is what we have to figure out, that if the given transformation is if you find somehow that this is a perfect differential, then this transformation is going to be canonical, and that is it is a perfect differential, so this is going to be a canonical transformation. So this is my canonical transformation. The second thing is we have to figure out what is the generating function. So this is my perfect differential. So if you integrate it, what I'm going to get is f equal to qp plus q cot p. Okay, so now we see that the first thing we can get, that if I say that f minus qp, because you see that this is my f. If from the table of generating function, this is my f, this is qp, so this is f minus qp is going to be my generator, this is going to be f3. So f minus qp, I have f minus qp here, and that is going to be q cot p. So this is q cot p is, this is equation I'm going to have, this is going to be f minus qp is my generator f3, and that is going to be equal to q cot p. But you know, sir, this generator f3 is depending upon a small q, capital Q and T, but this side I don't have a small p I have, but I don't have capital Q, I have a small q. So I had to transform this in terms of, so that my f3 depends upon a small p, capital Q, not in this this is depending upon a small q. So p is there, because p is there, but what I don't have, I had to replace this small p to capital Q. So I had to look for the transformation equation, that how small q and capital Q are related, so that I can use this equation here. So from the first transformation equation, if you remember that this is capital Q is related with the small q. So this is what I want. I want to have that relation between capital Q and a small q. This is what I have. So if I take the exponential both sides e to the power log q, and e to the power log is going to be 1 by q sine p. Okay, so now from here I can take this q is going to be here, and then sine p, and this e to the power q in the denominator, and then goes up, it's going to minus e to the power q. So now I have the expression of a small q in terms of the capital Q, and the second one is a small p, which is again the function of f3 is there, so it doesn't have any problem. So my f3, which depends upon a small p, capital Q and T, is my q chord p. So chord p is there because small p is there, no problem, it depending upon this small p. And then this q is now replaced by this expression, that is e to the power minus q sine p. So it is okay that I have my f3 depending upon a small p, and then I have capital Q also. So this cot p is cos upon sine, sine will cancel out, I have cos p. So you see that now my f3 is generator is e to the power minus q cos p, and that depends upon a small p and capital Q, which is the dependent of my f3. So the first generator f3 is going to be for this transformation is going to be e to the power minus q cos p. And you can find generator f2 and generator f1 or f4 also, depending upon you have to transform the dependence of that. For example, if I want the generator f2 for this transformation, so my generator f2 is depending upon generator f2 depends upon q, p and t. So I have a small q, p and t. But if my generator, this is my f2, suppose if my generator is my f2, this is my f2, okay, this is my this is my f2, but f2 depends upon q, capital P and t. So a small q I have here, but I don't have the capital P. Instead I have a small p. So I have to transform the small p into the capital P using the transformation equation, and that can be done on the basis of from this, because this gives me the transformation from a small p to the capital P. So I can write that this is from here, you can write this from this is small p is going to be the cot inverse capital P by Q. Okay, so I have f2 is qp plus q cot p. So q is there and it's a small p, I can replace with this cot inverse p by q, and q is there and cot p from here is ratio of p by q, this is p by q. So now this is going to be my f2 is going to be depending upon capital P and a small q. So that is going to be the capital P and a small q. So then my if my generator is f3, that is going to be e to the power minus q cos p, and if my generator is f2, that is going to be cot inverse p by q. In the same way, if you try to find your generator in terms of f1 generator, you're trying to find, because now you see f is depending upon a small q and q, but this is my qp plus q cot p. So a small q is there, but you need to find the relation between this small p and capital Q, small p, so that you get rid of this small p from the expression and your dependence comes upon a small q. And that can be done from here, that because you know that this is capital Q and the small p, a small p and capital Q are related using this relation. So this is you can do by replacing this. Okay. Now I will with this I think this example is enough for you, and in the next class we will continue from this second method of that, how to find out that we're going to apply the second method and the third method, Poisson bracket method and the partial differential method, to find out whether this transformation is going to be canonical transformation or not. Okay, so for now I'll take a leave, and then thank you very much.